Hi all, welcome back to our YouTube channel. Topic that we will be having look at today is from FRM level 1 and it's from paper 2 quantitative analysis and topic is machine learning and prediction. And stay till end of video because we will demonstrate one of the topic that is regularization on worksheet. And trust me, it's going to be very useful for you because world's best authors haven't done this so far. So stay till the end of the video. It would be very useful. In fact, share with your peers who are like aspirant of machine learning, which is like beyond your just FRM. So please do share with them as well. And please subscribe to our channel. It takes a lot of efforts to come up with videos like this. So these are the things that we would be covering. Mainly it's regularization and types of regularization. But to understand regularization thoroughly, you need a background of linear regression, underfitting and overfitting issues in your regressions. And then we can understand regularization well. And followed by brainstorming, we have just put in one question to test your understanding. And then as we committed that we will demonstrate it practically on worksheet. So let's understand first what is overfitting. See, before we start, you need to know that when we talk about machine learning, there are two types of data that we talk about. One is training data, which you put in the model, so that model gets some sense out of it, and it has some kind of predictive power. So that's training data, which is kind of input to the model in machine learning space. So just think of a hypothetical example. Say you have got 15 divisions in school for say any standard, and you want to conduct some analysis wherein you want to study what is a uh, relation between height and weight of students. So you don't have that much time and effort to conduct this thing for all the students. So what you do, you just take one random division which has a high number of students, and you just collect the data of height and weight, put that into the machine learning model. So that what that model will do, that model will try to understand how this moment of height with respect to moment of weight with respect to height is. So based on this pattern, what it will do, it will try to come up with some equation so that that equation serves as a model for further prediction. So then what you can do, you can just collect the height data. And so that's the main objective of regression. You want to predict something from the trained data. So what overfitting is like, you try to overfit your data, like the equation that you try to derive based on the input data is very specific to that model, not really. So it will perform very well for that sample, but when you apply it on other model, like you when you apply it to other divisions, so you notice that there would be very high variance. So this is a tested data wherein when you applied it to the other divisions, it ended up having very high variance. So overfitting is a issue wherein model works well for in sample data. So over there is a low bias. And when you try to work it out for out of sample data, in our example, when you try to apply it for other divisions, it ended up having more variance. So overfitting is a issue which works well for our training data, and it ended up having high variances for tested data. So, and for regularization, this is something which is a problem which regularization is trying to solve. So we mainly require to understand overfitting, but just for your understanding, so it you should be always open to learning. So we have put in underfitting. What is underfitting as well? So underfitting is kind of it's kind of low accuracy in terms of trained data as well as tested data. So see, for training data also it doesn't perform well. For tested data, it may or may not perform well. So underfitting is kind of low accurate model, but overfitting is kind of it. The accuracy is high when you test it on the training data. Accuracy is very low when you apply it to the tested data. So these are the two main problems that researchers or people in machine learning space deal with. So what the target is to get some kind of model that works well for your train data. See, this is the best model for in-sample data. So what we'll do, the fundamental of regularization is we will compromise bit of accuracy on the train data, but that in turn will give us more accuracy on the test data. So in the test data also your variance go down. So that's the key of the regularization concept. If you have got any doubts on this slide, please put it in the comment box. We would be happy to answer your queries, because if you understand this slide well, the rest of the stuff would be very easy for you. So let's understand how this regularization solves your this overfitting problem. So first of all, regularization is a tool that prevents your overfitting by including additional information. We use it in a regression to help model avoid fixating on irrelevant data too much. So as we saw that the target is to get some model which works very well for in sample as well as out of sample data. And motivation of regularization is, of course, these are the two major problems that researchers deal with. That is overfitting and multicollinearity. Multicollinearity is kind of a issue wherein if you have got more independent variables and those are correlated to each other. So that's the multicollinearity. Yes, before we go ahead, this is something our suggestion to students preparing for any competitive exams is. So you can look at picture. There is a screw that person wants to deal, and one person has a screwdriver, but still he's trying to deal screw with a spanner. So like you're putting an effort, but with the wrong tool. Rather, if this person put efforts with a screwdriver, it may get him good results. So similarly, for students, if you have got right mentors who are experienced, they have dealt with the things, and right question banks, right time and learning management tools, then like you can be a guy like a screwdriver this in this picture. Otherwise, most of the people what they do is mentioned over here. The person with spanner is kind of similar to the student who keeps paying fees repeatedly to the exam conducting bodies. Most important, on top of all, your precious time is a intangible loss, and you ended up having delay in your career starting. So act wise, and yeah. So let's look at, so we covered what is a regularization. So what are two types of regularization are ridge regression, it's also known as L2 regularization, and lasso regularization. So it's L1 regularization, that is a synonym for lasso. So let's look into detail what these are. So just recalling our previous slide back, we had issue of overfitting, which we want to fix using the regularization. So just recalling what is overfitting, a regression issue wherein regression model works very well for in sample data, but it doesn't work well for out of sample data. It gives you high variance, high error terms, or high uh, sum of, I mean, its error terms are super high. Residual sums of square, yeah. So just divided our page to categorize our stuff. So there are mainly two types of regularization as we talked about, but there is a third also that is called as a hybrid and elastic net, and it is a part of your FRM curriculum. And it's nothing but it's a hybrid of both ridge and lasso regression. And when we talk about this ridge regression, it's introduction of a penalty term. As I mentioned that instead of having zero errors, so for in sample data, instead of having zero error terms, fitting models in such a way that you don't have any error terms, what we do, we introduce a penalty term. Instead of having zero errors, we deliberately try to have some error terms. But what that will do is that will improve your out of sample regression. So that's where we introduce a penalty term, that is like, and we try to reduce the slope. So like in this, the slope may be high. You can see that your if your x changes, y is changing drastically. So we just try to reduce slope term, and the shrinkage penalty for large slope coefficient. So we try to reduce slope coefficients which are quite high. So if you notice that when you uh, when you just have the overfitting problem, your loss function may be just residual sums of squares. That is just the error terms, which you actually have the zero because you have fitted your model in such a way that your predicted versus actual data is same. So in general, it would be zero. But when we talk about risk regression, we just try to introduce some kind of penalty term, which is lambda times this beta I square, that is your slope term. So beta is called as a hyperparameter, just for your information. So instead of having it zero, you try to have some penalty term just to have the good good out of sample regression. So that's the ridge regression in short. If you understand this much also, this is sufficient from the exam point of view, but we will have the demonstration of this in worksheet as well. And Lasso, what they do is they also introduce a penalty term, but what they do, they try to make the slope coefficients of the variables, independent variables, zero, which are less important. Over here, you try to reduce impact of beta, but for Lasso, you target it to move it to zero. So mathematically, a loss function has or a cost function has a just a small tweak for Lasso. Instead of beta I square, you have mod of beta I. See, these are different things that researchers keep coming tomorrow. Even you can also have some kind of new regularization type. If you demonstrate that that works that works well with the empirical data. And finally, it's a elastic or hybrid net type of regularization wherein loss function incorporates penalty term from both. So you have something coming from ridged and something coming from lasso. So two slides, if you understand well, like overfitting, underfitting, and what we are trying to achieve by overcoming these two issues, and how that was covered in this slide. And just to test your understanding, small, very simple question has been put in over here. Say, just think that there is one model wherein it's say date, but it's a data, training data accuracy. So training data accuracy is 40%. So it's data. Okay. So for training data, that is model, the input that you are putting into the machine learning model is 50%, and out of sample data is 40%. So if you notice, both training as well as tested data don't have that much accuracy. So you need to have the proper name for this kind of issue. And second model is wherein you have very good accuracy on the training data, that is 90%. And when you try to apply that on out of sample data, it goes down to 60%. So exercise for you is to name the I mean which model has which issue. That's something you have to put it in the comment box. And yes, as we committed, we will demonstrate it practically. So let's have a look. Are you excited to see the practical demonstration? I believe it would be yes, because these kind of demonstration have been not given even by world's best author on FRM, CFA, or MBA space. So let's have a look. So the column AB is something which is a kind of it's a kind of a input data, tested data. Uh, I think it's head as a incorrect. So this is a trained data. Let me just correct it. So I think no, it's correct. So this is a training data wherein you collected the sample from the one division and you try to arrive at a model. So you arrived at this equation, which kind of serve as a model for your further prediction. You can just notice that R square is 1. And yeah, so on training data, your model is best fit. You have 100% R square, but when you try to test the data on the other out of sample data, say on other divisions, so this ended up having very high error terms. So if you notice, R square came down to 3% from the 100%. So out of sample is this situation. You have very high error terms. This is kind of a zigzag pattern. So over here, it was a perfect 100%, wherein your predictive versus the actual data was exactly same. So you had 100% in sample data, but out of sample is this problem. This problem is called as a overfitting problem. And how we try to fix it using ridge is by introducing this error term. We talked about that initially when we had in sample data, our RSS was 0, but instead of 0, we will try to have some number because we are trying to introduce some penalty term, but it will improve the regression power here. Like your R square will go up, your error terms will go down. So that's why we have introduced hyperparameter as one. This can be so. This is kind of a trial and error thing. In practice, people trial do a trial and error for which lambda the actual out of sample data is working best. So another term is beta I. So we had beta of zero point 0.5 slope term. So the square of that is 25. So if I substitute lambda and 1 and beta square as 25. So and over here we just have one independent variable. So we will have the loss term value as 0.25. So if I just plot the same in sample data using using this error term, if you notice, it had very high slope. The inclination of line is relatively high. But when I apply a ridged model, the inclination came little down. And if you try to apply this model now on your out of sample data, that will work very well. So this was a hypothetical data, which we try to demonstrate for our ridged regression. And yes, if you like the video, please do share with your peers. And if you are excited to have this kind of learning for your entire FRM curriculum journey, please do get in touch with our team. They will actually guide you and they'll connect you with the best tutors. Thank you. Stay connected with the channel and please do subscribe to our channel or share as much as possible. Thank you.